to monitor Earth and its climate.
Yes.
Can you hear me?
Yes, we can hear you very well. Thank you.
Okay, excellent. Great. Okay, здравствуйте. And before I start, I just want to say spasiba because it's been, I worked with Gareth at Scott Polar Research Institute, and I have a great affinity to Russia. I spent some of my childhood in Moscow, so I can't wait to come visit your beautiful city again once we can all travel again. So thank you very much for inviting me to talk today. So about me, my name is Anne-Marie Trofaier, and I work for the European Space Agency's Climate Office. Can you hear me?
Yes. Yes.
Sorry, I just had an interruption. That's fine. Good. My background is in the Cryosphere, so monitoring snow and ice. I actually did a PhD at Scott Polar Research Institute with Gareth on microwave remote sensing of surface hydrology in permafrost regions, and I spent some time also on the Yamal Peninsula. But that's quite a long time ago now. I know this conference is all about high latitude vegetation, and that's a little bit out of my comfort zone. However, I thought I might present something to you on what the European Space Agency is doing to establish an operational satellite system for monitoring our planet and its climate. So this talk really stems from some of the work that we're doing at the Climate Office in the UK, but also within the European Space Agency's Directorate of Earth Observation in general, of which the Climate Office is just a small element. So I don't think my video is on. I hope that doesn't matter. As long as you can see the slides, that's good. So the Climate Office is primarily in charge of running the Climate Change Initiative program. And the main objective of this program is to help characterize the Earth's climate and its change by creating long-term consistent error-characterized climate data records using the entire satellite archive. So what is a climate data record? Well, we define a climate data record to be a time series of measurements of sufficient length and consistency and continuity to determine climate variability and change. So these changes may be small and occur over long time periods compared to the short-term changes that are monitored for weather forecasting. Climate data records can be created by merging data from surface, the atmosphere, and space-based systems. So what does this mean? To understand why we're doing this, let me just take a step back and start with a brief history of international cooperation on monitoring the climate. So international cooperation for climate.
I'm sorry, if you are changing the slides, we are not seeing the slides.
Due to chlorofluorocarbons was a major concern. And in 1987, all 197 UN member states adopted the Montreal Protocol on substances that deplete the ozone layer. Now, as we all know, the ozone layer acts as a shield that reduces the amount of UV radiation that we receive at ground level. And in the mid-1980s, a large hole appeared in the ozone layer above Antarctica. And from space, we see this vantage point, and it lets us monitor variables such as atmospheric ozone. Space lets us monitor these variables.
Excuse me, Maria. I was supposed to see the first. I was supposed to go through the slides because we still see in the first slide.
Really?
Right?
Yes.
Oh, mine is
on slide 1.
Oh, I'm sorry about that.
Maybe if you can run the slideshow.
Yeah. because it was on my screen correctly. Maybe let me try it via the screen.
Yeah, what we see is your PowerPoint screen with slides on the left in very small scale, and just a clear slide on the main screen. So maybe if you can start the slideshow somehow.
Sure. I think maybe because I changed it to, okay, I know what to do.
Excellent.
Two secs. It's because I changed a, let me get out of this.
Okay.
I did apologies about that. I didn't want it to go across both screens, but that's fine. I can work this. If I do this, I'll go back to here, then do this. Sorry, talker, I see what you're saying. So hopefully you can see this.
We are still seeing the first slide. Maybe you can stop the demonstration and restart again, because I think Zoom may be showing the old screen.
Ah.
Mm-hmm.
Oh dear, this is what I was worried about. I'm doing it through the browser. So now I need to
know that
swap displays.
If you stop the demonstration, maybe that,
That if I go through here, do you see this?
It's not changing.
It's changing for me.
It's changing.
Oh, it is. Okay.
Yes.
Okay. I apologize about that. So let me just take you back to my little and go back to my main point about this was that we can actually monitor quite a few geophysical parameters from space that are important for the international community and important as well for climate. So in fact, you know, in terms of international cooperation on climate, it did not stop there. So in 1988, it was the UN Environment Programme together with the World Meteorological Organization that established the IPCC, the Intergovernmental Panel on Climate Change, which is arguably the most important scientific assessment of anthropogenic climate change. And it was meant to prepare a comprehensive review with recommendations on the state of the art of science and climate change. It was in 1990 that the IPCC released the first assessment report confirming the reality we all know that today emissions resulting from human activities are substantially increasing the atmospheric concentrations of greenhouse gases. But it was clear the world needed a global treaty to discuss binding commitments and targets for reducing these emissions. And it was at the Rio Earth Summit in 1992 that the UNFCCC, the United Nations Framework Convention on Climate Change, was signed. So the UNFCCC is the legal framework for negotiating international treaties, as we all know. But policy needs to be based on science, and the convention needed a scientific voice. And this is also when the Global Climate Observing System was founded. It was the task of the Global Climate Observing System, it's a bit of a mouthful, so we just call it GCOS. It was to identify the variables that need to be observed systematically to be able to characterize the Earth's climate and monitor its change. And this is also where this idea of essential climate variables stems from. It was at the climate conference in Bali in 2007 that it became apparent to the space agencies that we were behind the curve in terms of supporting climate science from satellite observations. So there was no dedicated program of the space agencies to support the necessary long-term monitoring activities. And this needed to change. What was needed were long-term multi-mission consistent, unbiased data sets of essential climate variables with relevant uncertainty measurements. So the European Space Agency set an activity in motion that would change the way we dealt with thematic data products and arrive at these climate data records. So this program is the Climate Change Initiative, and we call it CCI for short. And it's only one part of the puzzle for better understanding our climate system from space. Another part of the puzzle is the Copernicus program, which is a program of the European Union and for which ESA has been tasked to build future satellite missions. And I'll be talking about this in the second part of my presentation. But first, let me tell you a bit more about the CCI program, because this is what we do in the Climate Office. So out of there were 54 ECVs that GCOS identified, and only 22 of these we believe can be addressed from satellite data. So this is just a diagram showing you the ECVs that we believe we can monitor from space. So how does this program work? Well, we start with these GCOS requirements, and we ask ourselves what is necessary to monitor the Earth's climate from space, and what types of satellite technology can help us understand the climate, and how can we combine these different data streams to create long time series, eliminating any bias that would arise from these different technologies. Because of course the tricky part is combining data from different technologies over the ages. Sorry. Combining different technologies over the ages, because you might introduce a false signal. So you have to be very careful how you approach this. So we take the GCOS requirements for the ECVs and develop the algorithms, and then we also have a duty of data curation. So long-term monitoring requires appropriate data management, which we also address within the framework of the CCI. And if you're interested in working with the data, then please do visit our website, because all these data are free, free to all. So now, yeah, so you probably saw this yesterday in a talk. I'm just going to give you a few examples of the research output from my Cryosphere projects. So you will all be aware about the Arctic sea ice and how it's been decreasing. And so this graph is derived from satellite information we have had on passive microsatellites. So we've had passive microsatellites in space since the 1970s, which allows us to measure sea ice concentration, which is the percentage of sea ice within a given pixel of the Arctic Ocean. And of course, this can easily be converted into sea ice extent. And sea ice concentration and sea ice extent are both climate data records. So by looking at the trend in these data sets, such as sea ice extent, we can already see that, you know, things are not looking too rosy for the climate. But we can do more than that. Our satellite data help the climate modelers examine the robustness of the sea ice simulations from the latest generation of climate models, and so guide and inform future projections. So one of the aspects of the CCI is actually to create data that are relevant for the climate modeling community. We've also been doing some research into snow mass across the Northern Hemisphere. So here we combined, well, my team combined 39 years of satellite data to create a snow mass climate data record, which has been validated with ground-based snow depth measurements to arrive at a new bias-corrected data set that reduces the uncertainty of annual maximum snow mass from 33% to 7.4%. So this improved long-term climate data record of snow mass has enabled continental scale trends to be investigated. For example, according to my team's study, snow mass decreased by 46 gigatons per decade across Northern America. Over the time period is 1980 to 2018, I should say. Now, after yesterday, I thought I'd put in this slide. Here's an interesting parameter. Permafrost is, of course, a subsurface phenomenon. So we can't actually directly measure it from space. But as you will all be aware, it also underlies almost a quarter of the Northern Hemisphere. So in situ measurements are just not enough to monitor it at the hemispherical scale. We can't just interpolate and then extrapolate. But we need satellite information to inform us on this larger scale. So how does that work? If I just said that satellites can't monitor the subsurface. So in this community, often the approach is to look at changes in land surface features, but there's also another approach here, which is to use satellite-derived climate data records, such as those on land cover, land surface temperature, and snow water equivalent, which is also the parameter we use to calculate snow mass, by the way, from my previous slide. And to then feed those into a model, which then computes the ground thermal regime at different depths. So we can derive permafrost temperatures and active layer depths using model assimilation techniques. Of course, we still need the in situ data to validate our products. And indeed, field data are incredibly valuable to creating satellite-derived climate data records. So actually, if you have data from field sites across Russia that you want to make available to the community, you're always welcome to get in touch with me. And, you know, this holds true for the permafrost community, but any long-term monitoring is of interest to us. It's really, really useful data. Yeah, there's a lot more on the CCI in reality. I just presented a few scientific highlights, as they were, from the projects that, some of the projects that I follow. And I saw that the next talk, in fact, will be on the CCI biomass project. So I'm going to leave it there and move on to the second part of this talk, which is on the satellite landscape, or maybe should I rather say the spacescape in Europe today, and in particular the Copernicus program, as you will all know it already. So I suppose we are far enough into the age of satellites. As you all know, the first technological demonstration of a satellite, of course, was famously the Soviet Sputnik satellite, launched in 1957. So Earth observation satellites came a bit later, properly really in the 1970s. So maybe we're not that far yet into the era, but today at least we have more than 40 years of Earth observation satellite data. And hopefully I was able to show you just earlier how 40 plus years of Earth observation satellite data and clever programs such as the ESA CCI allow us to better understand our climate and see the trends that are happening in our climate system. Now, of course, the distinguishing feature of a useful climate data record is continuity. So what we are really looking for is an operational satellite system where we decide which types of sensors we need and make sure we have these in orbit, ideally in perpetuity, but that's another matter. Such a system has existed for meteorological satellites, but for Earth observation satellites, this was not the case. ESA's first Earth observation satellite EIS-1, which was followed by 2, which had a payload of a synthetic aperture radar, radar altimeter, and was there to measure ocean surface temperatures and wind fields. They were launched in 1991 and 1995 respectively. So you could say that the European Space Agency probably started Earth observation in the early 90s. But back then, in the 1990s, it became apparent that Europe didn't have a strategy for long-term satellite Earth observation. Basically, what was needed was to establish a program similar to what already existed for meteorological satellites, where satellites would be replaced by another to maintain a continuous long-term record. And yeah, this is exactly what the Copernicus program does. So it responds to the growing need for geospatial information services, not just for climate, but other environmental as well as security issues. And before I launch into this, I'm just going to show you a slide on the entire European space, because it's not just Copernicus. So at ESA, we distinguish between 3 branches. We have the science missions that are there to test the new technologies in space. So these are the missions that are pushing the boundaries of science. We have the meteorology missions that I mentioned earlier, which we actually build and then get operated by our sister agency, EUMETSAT, which is the operational satellite agency for meteorology. And then there is Copernicus, which are the satellites that we build and operate on behalf of the European Union. And it really is Copernicus that has changed how we observe how we do Earth observation in Europe. I'm sure you've noticed ripples that are felt across the globe. I've seen several presentations now that mention Sentinel-2. So it really was conceived as a program that would benefit us all. And so the current Sentinels are 2 satellite constellations in near polar orbit to fulfill revisit and coverage requirements. They carry a large range of technologies to monitor individual components of our planet. Yeah, this slide just shows the ones that are currently in orbit or will be launched soon. Of course, we start off with Sentinel-1, which is a C-band synthetic aperture radar mission. Sentinel-2, the multispectral high-resolution imaging mission. So this one will almost certainly be of interest, as it was even designed to better image vegetation. But of course, it has many applications. Sentinel-3 is a multi-sensor platform. So its main mission is to measure the seas, and it has a radar altimeter on it, a push broom imaging spectrometer, and a dual view conical imaging radiometer. But it doesn't just image the seas, it obviously also works on land, and one of my projects on snow actually uses Sentinel-3 SLSTR data to look at fractional snow cover on land. Sentinel-4 is a little different. It's actually a payload, not a satellite platform. And it will be placed on one of the Meteosat 3rd generation satellites, which will be placed in geostationary orbit. Then Sentinel-5 is another atmospheric mission looking at air quality, ozone, and UV radiation. In fact, the satellite in orbit at the moment is Sentinel-5P, the precursor, to test out the instrument. and Sentinel-5 itself will again be a payload on one of the meteorological satellites. And the last one on the list is Sentinel-6, which is actually due to be launched this Saturday, if all goes well. Sentinel-6 is a radar altimeter that is based on a long heritage from our US and French colleagues. It's the Topex, Poseidon, and Jason series continuity. Its mission is to measure the rising seas, and it will collect the most accurate global data on sea level yet. Sentinel-6 will also be essential to studies, for example, of sea level budget closure, and this is one of the CCI studies again. So coming full circle here to show you how the operational data will also filter into the climate data record and help us better understand the climate. So in this particular case, we're trying to understand whether observed sea level change is explained by the sum of its components. So by looking at changes in land ice, but also looking at the sea surface temperature and the steric component of the oceans, and to see whether if we sum all these contributions, whether they equate to the observed trend. So I'm going to go back to Sentinel-6. So it should be quite clear why this mission is so important for us on understanding how climate change is affecting sea level rise. And we're rightly quite proud of the satellite, as it's also a collaboration between ESA. Well, it's obviously a collaboration between ESA and the EU because it's a Sentinel, but it also includes our partners at EUMETSAT, as well as in the US and NASA and NOAA. So it's one of those projects where we can see that the space industry really can transcend borders, and we're always very happy to collaborate. So as I said, Sentinel-6, Michael Freilich is the first satellite, is going to be launched from California on Saturday, 21st November. So if you're interested in watching the launch, then please do. We woke up this morning to a failed launch. So these things are never straightforward. We can only hope that Saturday's launch will go better than last night's launch of CEOSat. It's always a very, very intense moment. So much energy goes into building these satellites. Finally, there's more to come, is how I'm going to end the story. We're busy planning a new Copernicus missions, the Copernicus expansion program. And there will be more satellite sensors with different sensors, sorry, that will complete our space observatory. So the first one here, which the EU is very interested in doing, is the Co2m mission, which will be which uses an infrared instrument to measure the concentrations of carbon dioxide and methane and nitrogen dioxide in the atmosphere. So it's another atmospheric mission. But we also have LSTM, Copernicus Land Surface Temperature Monitoring Mission, which will measure the temperature of the land surface, which of course has particular interest in agriculture. But also, it'll be interesting to see, it's also supposed to support studies that determine the amount of evaporation. So we also be able to make more accurate predictions of drought in the future. So that's actually quite very important in terms of climate monitoring as well. So the next one on this list, Crystal, is actually one of the ones that my community are interested in. It's the next mission that's very similar to the current Cryosat-2 mission, the Copernicus Polar Ice and Snow Topography Altimeter, which is designed to, or will be designed is rather the word, will be designed to determine the thickness of ice masses in the Arctic and Antarctic, and to measure the thickness of sea ice. And then there will be a mission, SIMA, which is a imaging microwave radiometer, which will monitor the ice cover and surface temperatures of the ocean. So this is one that's really interesting to the sea ice community, to continue the existing climate data record that I showed you earlier. And I know that many in the sea ice community are actually very worried that this SIMA satellite might not be launched, that there might be a gap between the end of the current radio passive microwave missions and the SIMA satellite launch. And these things are very much on our mind if we're thinking in terms of continuity for climate data records. So the agency is aware of all this, and we just need to do our best to make sure we arrive there and can deliver on time. Then there's two more on this list, Roselle, which is an L-band SAR. And again, this one has many applications, operational applications in agriculture, forestry, but also for maritime services. So again, sea ice, from my point of view, sort of more in terms of looking into supporting the sea ice services for shipping. And lastly, we have the CHIME, which is going to be a hyperspectral imaging mission, which will perform imaging spectroscopy on the land surface to support applications in agriculture. Now, I'll finish with this final forward-looking remark. So we've come a long way since the early satellites, and computational advances have allowed us to return to the historic data and pull out more information which we need to better understand our planet's climate. But this truly is the age of satellites, where we are seeing the shifting lines in Earth observation, because we're moving from mission dedicated to scientific curiosity to those that are designed with certain applications in mind, and support for services that will provide strategic, social and economic and environmental benefits. And that is exactly the Copernicus program, and what the Copernicus program is here to deliver on. So with that, actually, probably quite a short presentation, but I would like to end. So if you have any more questions, please let me know.
Thank you very much, Anna Maria. Now we will welcome questions. Коллеги, пожалуйста, вопросы. Анна Мария.
Okay, we're going to see whether we have any questions. I'm going to translate questions into English if they are in Russian, because Anna Maria is using a web version of Zoom and she doesn't have the translation function there.
While people are thinking, Gareth wishes you good luck for ESA, for Sentinel-6.
Yeah, I mean, we need it. It doesn't often happen that you get a failure, but we all woke up to a failure this morning, and it's not good news when that happens. So hopefully Saturday will go well, because it is.
Yeah, we'll keep our fingers crossed.
Want to continue the record.
Yes. Коллеги, вопросы по поводу, может быть, по поводу проектов, которые...
Colleagues, do you have any questions to Anna Maria? Anything you want to know about current missions or future missions, about the projects that she covered?
Yeah, go ahead, Gareth.
Go ahead.
Anna Maria, thank you so much for this overview of what ESA is doing for us. I think everyone is terrifically grateful for the vision that ESA has here, and moving you know, satellite Earth observation from science into truly operational. You really tantalized me with the mention of the LSTM and the CHIME missions. When can we have them, please?
Okay, so the good news is, because these, of course, these are missions that all the Copernicus missions are requested by the EU. And the good news is we have agreed to go ahead with the first one of each of those. So there is agreement on that. And the way it also works is ESA pays for the first one, the EU pays for the rest. However, when can we expect it? I'm afraid it might be another, like, within the decade. It's still quite, you know, it's early. We've only just been given the go for going into the next phase of planning. I'm not on CHIME myself. I work on the Roselle mission. Well, I'm an observer to that group. So I can only tell you that it'd be, for Roselle, it would be towards the end of 2020s for the launch. But, you know, we want these missions, so they will be coming.
Great, thank you.
Yeah, this is good to hear. Коллеги, еще вопросы?
Yeah. I was just thinking, there's one other thing that one of my scientists mentioned the other day, that he would like to push for the next generation of the current Sentinels. So one of my scientists who works on snow, he really believes we don't have the right bands for Sentinel-3 SLSTR to be able to discriminate between snow and cloud. So I think there's also a lot of thought going to go into that, whether we need to rethink which bands to put on the next Sentinel-3, next generation Sentinel-3, and that sort of thing. So it's continuous development, and in fact we need the feedback from the scientists. I don't do the research. We need the feedback from you scientists to tell us, you know, we really just can't see a difference between this snow pixel and this cloud pixel, but if we had the appropriate bands, then that would be possible. That's the sort of thing that the Space Agency needs to know.
On this note, when you were talking about the snow studies, you mentioned that the uncertainty in snow volume estimates on land have been reduced to 7%. I was wondering about dense forests. Do forests interfere with your assessments of snow, and how do you deal with them?
Forests are tricky, certainly, especially for snow water equivalent. They do deal. I mean, we do have appropriate transmissivity maps that go into these sort of calculations, but that sort of thing will be taken into consideration in the uncertainty characterization. So you will probably see higher uncertainty in forested areas than you would see in just the barren areas. I can put you in touch with the team who published that publication. So if you'd like to hear a bit more about that, that might be useful.
Thank you very much, and I'd like to thank on behalf of all of us for this insight into the Copernicus program and these future perspectives. And I'm sure some of us will be in touch with you as a scientific feedback on what we want to see on the future missions. So now I think
yeah, do please, yeah.
Yeah.